Today we'll calculate E in slices. Now we know the number E. E can be computed to a lot of digits. The formula for E is pretty simple. It's just the sum of the reciprocals of factorials. But what does the number E mean? Can we draw a picture of E? We can draw a picture of pi. But E is different. Let's give an example of a bank that does not pay interest on interest. This is a thought experiment. Suppose the banks in a particular land pay interest, but they don't pay interest on interest. The interest goes into a separate account that just accumulates over time like pennies in a piggy bank. It'd be easy to calculate how long it would take to double your money. It would be just the reciprocal of the interest rate. So 4%, it would take 25 years for your money to double. We'll call this time period T, capital T. How much more would you earn if your interest earned interest over that time period T? Well, it turns out it's E instead of 2. Now, suppose there's a loophole in that land. While the banks don't pay interest on interest directly, you can redirect your money to another account. We'll call it a level 1 investment account, and that account does pay interest. Of course, you would have to redirect the interest on a level 1 bank to a level 2 bank to get interest on that, and so on. So how much money will be in each level M investment account at the end of the time period T? Let's go to a spreadsheet and do a calculation. Okay, in this spreadsheet, we'll calculate the amounts in each level M account. So first, the interest rate is 1 over n. In this case, n is 10,000. It could be any number. The amount in A0 is always 1. The interest payment is always the interest rate times the number to the left. The amount in the level M plus 1 account is always the sum of the numbers in the interest rate M account. Now the first few calculations, first few rows are all zeros because it takes a while for the numbers to filter through the system. There's a bit of a delay. If we bring it down to the first 20, we can see some numbers here, but they're very small. They add up to a lot by the end, though. The blue circle means the Excel is calculating. It's calculating 10,000 rows. It takes a little bit of time for Excel to do that. Okay, now it's calculated it. Let's go down to row 10,000 to see what the results are. If you look in the H column, we see a number 0.49995. That should be theoretically 0.5. The reason why we don't get exactly 0.5 is the delay by a half a day issue. We'll talk about that a little bit more later. So when we sum up those, we get a number for E. If you notice it very quickly, I'm going to compare it with the theoretical values, and you'll be able to see the difference. But we did get a number close to E, 2.0 718, which is good, but that's the extent of it. All the other digits are useless. The difference is 0.0001, which makes sense. It's 10,000. We'll calculate the reciprocals of the coefficients, compare the theoretical with the computed ones to see how big the error is in each level. So you can see that the error is getting progressively bigger. By the time you get to 6, you see 720 versus 721, or 7, you 540. Use some formulas for the sums of consecutive integers raised to powers in a calculation of each of these slices. Here's the formula for the sums of integers, and then for integers squared. Each one has its formula. What we will do is we'll compare the numbers on the left to the numbers on the right to see if they make sense. We're going to compute these sums of consecutive integers raised to powers. The formula for the power is easy. We just take the integer and raise it to the power. Use a little dollar signs here to make sure that we're identifying the right number. And then the sum is just a running sum. Easy to compute. Just the number above plus the number to the left. And these formulas, they're exactly the formulas that were in that slide. This first one is 1/2 n times n plus 1. We're going to bring that number over and modify it. In this case, we'll square it to get the third column. This one will raise it, add another term, a 2n plus 1 term, and change the coefficient to 1/6. And then we're going to use this number in the last column. We'll change that to 1/30 and add a 3n squared times plus 3n minus 1 term in there. Bring those down. Okay, we're going to check these numbers. They seem to be the same. I trust the math, but this is trust but verify. So what is the amount in a level 2 account after the time period t? Well, on the first day you don't receive a payment because the money went into the level 1 account too late to get a payment. On day 2, however, you get the first payment, which is the interest rate, times 1 day's worth of interest in the level 1 account. On day 3, you get another payment, which is the interest rate, times 2 payments in the level 1 account, and so on. On day N, the account receives the last payment, which is the daily interest rate of 0.0001 times the amount in the level 1 account, which is 0.9999. So this formula just says what the previous one said in words. This says it in mathematically. It's the interest rate times T. What is the amount in level 2 account after N days? You sum up the interest payments. And this is where the sum of consecutive integers comes in. We have a formula for that. Now notice the minus n. That means that's because we didn't get the last payment in time. We have to subtract it off. Now when we multiply through, we get 1/2 minus 1 over 2n. That's the 0.4995 that we saw in the spreadsheet. This is the one time where we'll calculate the exact value of an approximation. In general, we won't try to do that. What we want is the number 1/2, the theoretical limit. So let's go to the spreadsheet and see a picture. Okay, on the left are the interest payments from the level 1 account. On the right are the sum of those payments into the level 2 account. The orange dot on the right corresponds to the sum of the orange area to the left. And that's why you get a quadratic graph on the right. It's the area under a curve. This is like an integral. And you can see how the curve progresses. So the delay by 1/2 day problem. This is a blow up of that picture of the triangle underneath the interest rate curve. The orange triangle wasn't really a triangle, it was a stair step. You couldn't see it because there were so many stair steps, but when you blow it up and see just the first few terms, you can see there's a little missing black triangle. That's the delay of 1/2 day of interest. Basically, what happens is that your interest only gets delivered at the end of the day, not during the day. You miss out on some interest on interest because of it, and you lose some value because of it. In general, though, we're not interested in calculating that missing money. We're not going to try to calculate it. We're going to calculate the exact solution. So what we'll do, we'll approximate each level n+1 account as discrete payments, and then let n approach infinity to calculate the exact value. So what is the level 2 account after T% of all days? In this case, we're going to treat that orange triangle as a real triangle, and the area is 1/2 t squared. That's, in fact, the integral under a curve, if you know calculus. But geometrically, you could see it the same way. What is the amount of the level 2 interest payment after k days? So it's the interest rate times 1/2 t squared. A2 is 1/2. K minus 1 over n is the t. What is the amount of the level 3 account after n days? It's the sum of the interest payments. That's where you get the sum of the square root of integers. And we get, we can use our formula. The minus n squared term here is that we got the last payment too late to count it. When we multiply it out, the only term that's going to matter is the a2 over 3 term. The other terms are going to be small as n approaches infinity. So a2 is 1/2 times 1/3, we get 1/6. Let's go back to the spreadsheet and see a picture. Okay, this is another area under the curve graph, but this time on the left is our interest payments from the level 2 account that go into the level 3 account. The level 2 account grows quadratically. The level 3 account grows cubically. That's the area under a quadratic. So see how rapidly the Okay, what is the amount in the level M account after t% of days? This is the graph of the little bars, each of a height x to the m, times the width, which is the difference between time periods. When we sum them up and take the limit as n approaches infinity, we get 1 over m plus 1. That is the calculus result. We will not prove that here. We'll just take it as a given. But what we will do is show that if you accept this result, we can calculate the area from 0 to t. We'll use a substitution. The substitution that we'll use is that y is equal to t times x. When we plug that into the formula, we see that the t to the m plus 1 term factors out of it. And then when we take the limit as n approaches infinity, we find that it's t to the m plus 1 over m plus 1. That could be derived using calculus, but we didn't have to use calculus to derive this result. Okay, what is the amount of the level 3 payment after k days? It's the interest rate, 1 over n, times a3 times t cubed. And then the level 4 account after n days is the sum of these payments. And then we see it's the sum of consecutive integers raised to cubes. We have a formula for that. We have to subtract the last payment because it came too late, similar to the other calculations we did. And when we multiply it out, we're not going to bother multiplying it out. We already know that only the first term matters. The O of 1 over n just is shorthand for a bunch of terms that are small because they're 1 over n terms. And we're not going to bother multiplying it out. So we get a3 over 4. a3 is 1/6 times 1/4 is 1 over 24. So what is the amount of the level M interest payment after k days? This is the calculation that we will not prove. We'll just kind of go through the math, but we'll say at this point we're not going to prove that it's 1 over m plus 1 because that's a calculus result. We'll just assume that's true. Now we can use this to sum up all the interest payments, all the accounts, and we get the exponential function. When we plug in 1, we get E, which we should. When we plug in 0.5, what do we get? Well, that's got to be square root of E. But that means there's 2 ways to compute the square root of E. Do they both come up to the same number? Well, they better. Let's go to the spreadsheet and verify that each of the 2 ways of calculating the square root of E gives you the same value. Okay, this spreadsheet will be a calculation of the exponential function. Column C is 1 over k factorial, so that's easy to compute. The D column is the power of x, so it's x times the number just above it. Product is the product of the coefficient and the power. The sum is the sum of each of the terms. We'll bring that down. For 50 terms, we won't really need 50, but we want to have plenty. And that gives us a good number for E when we put in x equal to 1. Delta will be the difference between the theoretical E and the number calculated via the power series. So in this case, 0.5, we're going to raise that, square it, and see if we get E that way. And we do. We'll also calculate E to other powers and see how this method calculates it. Notice that for e to the minus 4 and e to the minus 8, we get an error. That's because, well, e to the minus 8, the numbers are very large in the product column, but the sum column end up being very small. That's a recipe for disaster. You'll never get a good number that way. Okay, get back to the question of why E. Well, maybe a better question is why T, where T is that time frame to go from 1 to E. You see, different time frames correspond to different interest rates. And T is the one corresponding to an interest rate of 100%. And that turns out to be the simplest. Thank you.